relatively quick one. So, in right triangle trigonometry, there are what we call special triangles, and oftentimes we just think of those as special angles in unit circle trigonometry. So, with So, when we're thinking about right triangle trigonometry, what we can think of is, first, let's go ahead and start with an equilateral triangle. And let's go ahead and say that the length of each of the sides of the triangle is 2x. Right. Now, it's an equilateral triangle, which means that each of the sides has the same length, but also that each of the angles has the same length. So if each of the angles is theta, that means that theta plus theta plus theta is equal to 180 degrees, and therefore 3 theta is equal to 180 degrees. And with 3 theta is equal to 180 degrees, we can divide both sides by 3 to get the theta is equal to 60 degrees. If we do the same process but with radians, then we get that 3 theta, 3 theta is equal to pi, and therefore theta is equal to pi over 3. You might be able to see a little bit why it's easier to work with radians, because we can just do pi over 3 instead of having to think, okay, what is 180 divided by 3? But either way, we're doing the triangle right now, so let's go with 6 degrees. So either way, let's go ahead and say this angle is 6 degrees. Now, imagine if we were to drop a line from one of the corners down to the very bottom. Now, although this is a little bit of a not very neat sketch, so it may not be very clear, but when you drop a line from a vertex of an equilateral triangle down to the bottom, what you get is something that splits the side in two. And therefore, although the total length of the whole length of that side is 2x, the length of just this side, I will do a different color. So just this side is x. But the length of this whole side is still 2x. Now, this is a right angle, and it's 9 degrees. Therefore, the length of this final angle must be, well, what must it be? Well, 90 plus 60, 100 minus the sum of this angle and this angle has to be equal to whatever the other angle is. And so 90 plus 60 is 150. And so 180 minus 150 is equal to 30 degrees. 30 degrees is also equal to pi over 3 divided by 2. So in radians, this is equal to pi over 6. And so we have what we call a 30, 60, 90 right triangle. Now, what we can see is that the length of this side is x, right? The length of this side is 2x. Well, what's the length of this side, the height, be? Well, let's use the Pythagorean theorem. So we have x squared plus something, let's go ahead and call it h, plus h squared, square root of that, or actually let's avoid that for now. X squared plus h squared is equal to, what is 2x squared? Well, 2x squared is going to be 2 squared times x squared, which is going to be, what is 2 squared? That's 4, because 2 times 2 is 4, so this is going to be 4x squared. And so, to get this, to simplify this a little bit, let's subtract x squared on both sides. And so that way, this cancels out, and we get, what is 4 minus 1? That's 3. So we get h squared is equal to 3x squared. Now, there's one final step, and that is to take the square root of both sides. And so what we get is that h is equal to square root of 3 times x. Oftentimes, we write that in the other direction as x square root of 3. So people don't think that the x is actually under the square root sign. So h is equal to x root 3. And so what we have is that if we have any 30, 60, 90 right triangle, and one of the sides is length x, then, and if the side adjacent to the 60-degree angle is x, then we know that the hypotenuse is equal to 2x, and that the opposite is equal to x root 3. Oftentimes, we just think of when x is equal to 1. And so when x is equal to 1, what do you get? When x is equal to 1, what do you get? Get 1, 2, and just square root of 3. And so what this means is that we actually don't have to try and think of the ratios of the sides of a specific triangle. We don't actually have to build the triangle. If someone asks us, hey, what is the cosine of 60 degrees? If someone asks for the cosine of 60 degrees, well, you could just go ahead and say, well, it has to be the adjacent over the hypotenuse, right? And so that would be 1 over 2, which is equal to 1/2. If someone asks for the sine of 60 degrees, then you could do the same thing and refer back to the triangle and get that it's, hey, the opposite over the hypotenuse, which would thus be root 3 over 2. Now, remember that when we rationalize something, we only rationalize it if we have a square root in the denominator, right? And so we actually don't need to rationalize this. And also, we can actually do the same things if we're computing the sine and cosine of 30 degrees. So if you were to imagine rotating this triangle, then the adjacent to 30 degrees here would be root 3, and the opposite would be 1. And therefore, the sine and cosine are actually just flipped. So sine of 30 degrees is equal to 1/2, and cosine of 60 degrees is equal to root 3 over 2. This is one of these, what we call special triangles. 30, 60, 90, and it's often called just the 30, 60, 90 right triangle. So 30, 60, 90 right triangle. The other one is something we actually went through in the unit circle video. But let's go ahead and go over it again, but with the right triangle trig this time. So if you imagine an isosceles right triangle, the angles have to be equal, right? And so that way you have 45 degrees, 45 degrees. Let's go ahead and say this has a length of x, and this has a length of x because these sides also have to be equal. Then what is the length of the hypotenuse? Well, by the Pythagorean theorem, it would be x squared plus x squared is equal to, let's go ahead and say c squared. That way 2x squared is equal to c squared. And so c squared over 2. And then, oh, wait, 1 second. I just realized I'm solving for the wrong thing. And so we just have 2x squared is equal to c squared. And instead of doing anything else, we can just say, hey, wait a second, just take the square root of both sides. So what do you get? Well, the square root of x squared is equal to x, and is equal to x right now, because we can't have a negative one, right? Because even though negative x times negative x is equal to x squared, you can't have a triangle where one of the sides has a negative one. So we have x times, well, what is the square root of 2? Well, it's not a number we can write very nicely, so we just write it as this. X root 2 is equal to c. So when you have a 45, 45, 90, what do you get? You get x root 2 as lengths. Oftentimes, the way this information is basically summarized is in a chart of cos theta and sine theta. And so let's make a little chart. And so 30, 60, and 45. So let's think of the actual triangles for a second. If you think of the triangles, then for 30, 60, what do you get? Well, remember that, and let's just go ahead and set x is equal to 1 for convenience because the ratios will stay the same no matter what. Then what do you get? You get 1 here. You get root 3 here. You get 2 here. And so the cosine of 30 degrees would be the adjacent to 30 degrees, which is root 3, divided by the hypotenuse, which is 2. So is equal to root 3 over 2. The cosine of 60 degrees would be the adjacent there, which is 1 divided by the hypotenuse, which is just 1/2. And so if we think of a 45-degree right triangle, 45 right triangle, and what do we get? We get something like this. 45, 45. You get x, or just, sorry, we're saying x equal to 1. So you get 1, 1, square root of 2. And then the adjacent over the hypotenuse is equal to 1 over root 2. And again, teachers will come after you if you do not rationalize the denominator. And so let's do that. Let's say that's equal to root 2 over 2 times 1 over root 2, which is equal to root 2 over 2. Now, in this case, the adjacent and the opposite are actually equal. And so the sine of 45 degrees is also equal to root 2 over 2. And what is the sine of 60 degrees? Well, look back here. The sine is the opposite of the hypotenuse. And so it would essentially be the other cosine. So if the sine of 60 degrees is root 3 over 2, and the sine of 30 degrees is 1/2. Now, and if you want the tangent of theta as well, well, I'm actually going to leave that as one last practice challenge problem for you. Finish this table for tangent of theta. Okay? So that's the problem. I'll just leave up to you. Do remember your or remember the relation between sine, cosine, and tangent that we did in our unit circle video. Okay?